Hi folks, so if you've watched my prior videos, you know I recently developed and installed an instrument to help me understand soil moisture dynamics using temperature and capacitive soil moisture sensors at various depths in a shallow basin. Details of the instrument are summarized here with the build and programming links shared in my last video. Today, I'll summarize the data collected by this instrument to include simulating rainfall events in order to see how the instrument responds. Now, for those of you who just want a summary of the most recent data and lessons learned, I'll summarize it next so you don't have to watch the whole video. I'll include a deeper dive into both my methods and data after this cursory summary. So, based on prior experiments, we now know that capacitive soil moisture sensors that meet quality assurance criteria realize a repeatable signal response of 280 in water up to 785 in air. Most makers will use the signal for wet and dry endpoints to develop a linear curve for approximating soil moisture as a function of signal response, with the sensor reporting lower numbers in moist soils and higher numbers in dry soils. Based on soil column experiments summarized in prior videos, I've determined these sensors do not respond linearly to water losses. This can realize an overestimation of soil moisture where low signal response incorrectly suggests high or stable water content. As such, I would use caution in using these sensors for little more than flagging an increase in soil moisture content resulting from infiltration to a given depth. This table and graph summarizes temperature data collected at various heights and depths over and under my basin over the course of 16 days, with no moisture encountered or introduced at the site. In summary, temperatures at ground maxed out at about 153 degrees Fahrenheit, when ambient temperatures in the shade were at about 100 degrees Fahrenheit. At a depth of 1 foot, maximum temperatures dropped to just about 90 degrees Fahrenheit, with little standard deviation. Baseline data also demonstrates that capacitive soil moisture sensors are influenced by diurnal temperature patterns. In southern Arizona, sensors buried at a depth of 3 inches in a silty clay soil can yield up to a plus or minus 25 unit signal variation during the summer at a constant or dry soil moisture content. That same sensor operating in a silty clay can yield a drop of 140 to 160 units in response to simulated storms. This suggests these sensors may be useful for monitoring infiltration at various depths in response to a rainfall or irrigation event. However, I suspect the nonlinear shape of their response curve limits their use in that they will likely underestimate soil moisture loss as a soil column dries out. Temperature sensors placed at ground level and 3 inches above ground will report up to a 20 degree Fahrenheit difference in dry conditions during the summer. That difference is halved to 10 degrees Fahrenheit in response to a simulated 2-year 15-minute storm. The change results from air temperature at ground staying flat even as general ambient air temperatures are increasing. Finally, sensor disturbance can impact capacitance and temperature readings. So if your sensors are attached to a staff or rod in the ground, be careful not to move your sensors when you're servicing or downloading a data logger that's attached to the same staff. Since this latest experiment will be the first of many, I've created this playlist for tracking the same over time, for which I'll include a link in the description of this video. So for those of you who haven't seen the last video, I'll do a quick recap. The instrument includes a BME 280 air temperature sensor located about 28 inches above ground. In addition, we have a DS18B20 temperature sensor at about 3 inches above ground, and another temperature sensor located at ground. And we have 2 more temperature sensors at about 6 inches and 12 inches of depth. And finally, we have 3 capacitive soil moisture sensors at about 3, 9, and 15 inches below ground surface. In response, I've received some comments noting that capacitive soil moisture sensors are actually not very useful for monitoring soil moisture. And frankly, I agree. Specifically, there are quality assurance issues you have to be aware of when purchasing these sensors. And they also have a tendency to over-approximate soil moisture for timing irrigation, details of which are summarized in these 2 videos. Having said that, I had a bunch of these sensors on hand and had already sorted out a few of them for quality assurance. These were easy enough to incorporate into my setup just to see if there are any redeeming qualities we might realize from the collected data if we couple them with other factors such as rainfall and/or temperature sensors. So with that background out of the way, let's talk about the first 2 weeks of data collection by this instrument in the middle 2 weeks of June. And I should mention that we had no rainfall during this period, and temperatures during the day maxed out at about 100 degrees Fahrenheit. And here's what the temperature data looks like with the results showing a diurnal profile, which is what I would expect from this outdoor installation. Now this is a lot of data, so let's zoom in a bit to see if we can clearly see what's going on with temperature. And here's that close-up. This isn't bad, really. The temporal resolution of 15 minutes for sampling is fine enough to clearly capture the temperature dynamics for the various temperature sensors. However, this is still a little too much for me to clearly understand what's happening in my uncovered basin, so let's break it down a little bit more. Starting with air temperature, you can see that the sensor is registering temperatures topping out at almost 120 degrees Fahrenheit for the entire period of record. That's actually much higher than what's being reported locally, with actual temperatures hovering around 100 degrees in early June. So why is this bias here? It's likely the sensor is capturing radiated heat from the ground as a result of only being 28 inches in elevation. It's also likely the sensor is capturing heat from the adjacent retaining wall a few feet behind the sensor. That's okay, but these are factors I should recognize in my data. As noted in the comments section of my last video, I could probably improve airflow around the BME 280 by drilling a few holes around the cover, and it's just something I forgot to do after the installation. Things come up and sometimes you drop the ball, but that is something that I'm going to be doing, is drilling a few extra holes in the cap so that airflow is a little bit more representative around that sensor. Now, 120 degrees Fahrenheit is high, but not nearly as high as the maximum 134 degrees registered by the sensor located only 3 inches above the ground. This confirms that the bare soil is likely radiating heat that's registered as I get closer to ground elevation. At ground, the maximum temperature soars to 152 degrees Fahrenheit, which is just under the 158 degrees needed to fry an egg. However, as I start moving underground to a depth of 6 inches, the extremes are quickly buffered with my max temperature registering only 102 degrees Fahrenheit. It's also interesting to see how the temperature profile at depth lags what's taking place on the surface and the air, which is reasonable given the higher specific heat of the soil mass. And when I reach a depth of 12 inches, the temperature extremes are almost totally muted, with a max of 91.4 degrees Fahrenheit and a very low standard deviation of about 1.5 degrees for the full data set. Now, what about soil moisture capacitance? Here you can see that those sensors also realize a diurnal pattern given the influence of temperature on capacitance. And here you can see that if I focus on the shallowest capacitive soil moisture data at a depth of about 3 inches, and compare it to temperature at the ground, there's definitely a temperature influence on sensor response by about plus or minus 25 units at that depth. Knowing that temperature can influence these readings is good background to have when formally using these for irrigation management. So now it's time to simulate some rainfall, but my watering can is missing a diffuser. This must be a common issue since I quickly found one that matched my watering can on Thingiverse and then printed it up for the first experiment. This diffuser will help me simulate rainfall more accurately than if I simply apply a hose to the basin. In terms of how much water to apply, I use the measured area for my basin and an appropriate rainfall depth for a high probability event as reported by NOAA, in this case a 2-year 15-minute storm. I then calculated the volume of water that should be distributed on my basin by my watering can to simulate that high probability rainfall event for a summer monsoon where I live here in Tucson, Arizona. So I'm just about done distributing about 3 gallons of water, June 24th at about 10:15 by the time I'm done doing this. So this has been distributed around the sensors, and this should be realizing some changes on the capacitive soil moisture sensors as well as my temperature and humidity readings. And I'm doing this at night so that the water has an opportunity to infiltrate rather than evaporate. All right, folks, it's June 25th, 9:30 a.m., and I just wanted to show you what the ground looks like around the sensors in daylight since I wetted this at night. So I should have gotten some good infiltration from that little simulated rainstorm last night, and we'll see how that impacts the instrument. Okay, folks, and I just checked the dashboard, and it says that the temperature here in the shade is about 108 degrees Fahrenheit, so it's been a pretty warm day. It's been about 2 days since I did the last simulated rainfall event. The sun's come down pretty much, so I'm going to go ahead and do another little simulation and see if I can get that wetting profile to move down to the deeper sensors a little bit. And before I add the water, you can see that things have dried out pretty well, at least on the surface. We've had a couple pretty warm days, so let's go ahead and throw some water on this. Slow and steady, but should make a difference, hopefully. And I'm doing this a little bit earlier in the day just so you can see that the site is in the shade right now, that I'm not putting the water on the sensors directly, but I am getting it distributed around in the basin. So here's the capacitive soil moisture data encompassing the period between June 21st and July 2nd for all three sensors. One thing you'll notice immediately is this change in the signal that happened when I did my first data download on June 23rd. Note two things happened. First, I lost most, if not all, of the diurnal sensor response on all three sensors. And second, the signals for all three sensors dropped significantly, yielding a minimum change of 105 units for the sensor located closest to the surface. This is obviously a problem, likely resulting from the sensors being slightly disturbed when I was opening and closing the electronics box attached to the staff for the same, with movement of the box amplified by the staff, which is acting as a lever. This suggests that capacitive soil moisture sensors are sensitive to the slightest movement and should be disturbed as little as possible to ensure consistency in long-term monitoring. To help us focus on what's happening 3 inches beneath ground, let's remove the other two sensor series from this graph and focus on the simulated rainfall events. Here you can see that on June 24th, there was a significant sensor response associated with the first simulated rainfall event, and that the sensor responds again to the second simulated rainfall event on June 26th. Note that the other two sensors located at a depth of 9 and 15 inches detected limited or no moisture from the simulated rainfall events. This suggests that capacitive soil moisture sensors may be useful to monitoring the progression of an infiltrating wetting profile resulting from rainfall or irrigation. Next, let's take a look at temperature data for the same period. Here's the data collected between June 21st and July 2nd. Here, you can see some noise in the temperature data was realized when the data logger was opened and reset on June 23rd for my first data download. I'm not clear as to why temperature would be as sensitive to movement of the instrument, but it's obvious that disturbing and resetting the data logger did have at least a momentary effect. And here are the times for the two simulated rainfall events. Next, I'm going to remove the data for the deeper temperature sensors to see if anything of interest pops out in the ambient air column above the basin or the shallow soil profile. In doing so, I'm going to focus in on this part of the graph right here, just to make any changes a little bit more visible. And here's that data zoomed in. This red line splits the graph to capture the period before and after my simulated storm events that were initiated on June 24th. Of interest, notice that ambient air temperature at a height of 28 and 3 inches above ground, captured by the blue line, is increasing. This matches what was taking place in our local weather reports, showing a substantial increase in air temperature as we approach the month of July. However, also notice that an increase in ground temperature is effectively buffered after the two simulated storm events. In fact, the temperature drops from 150 to about 140 degrees Fahrenheit. As a result, the difference between ground temperature and air temperature, measured 3 inches above ground, is effectively halved. This is more clearly seen if we zoom in on the range above 100 degrees Fahrenheit. Here you can see that the increases in air temperature demonstrated by the orange and blue series is buffered at ground level, likely due to the conversion of heat energy into evaporation. The data suggests that this buffering halves the warming of ground surface that might otherwise take place in the absence of water, from 20 degrees to 10 degrees Fahrenheit. If I'm reading the data right, this demonstrates that soils containing moisture can cool themselves through the evaporation of that moisture over time, similar to a human that cools itself by evaporating sweat on its skin. Now the next question is, how long does this effect last? Now, if I incorporate another 4 days of data, I can see that the difference between ground and air temperature grows to about 15 degrees, due in part to a marginal rise in ground temperature, even as temperature in the air column above the basin is decreasing. Now, I recognize these results are qualitative at best, but really this isn't rocket science. It's obvious that water will have a cooling effect on surfaces, as anyone can sense by walking on some warm bricks that have been sprayed by hose water. The question I have is, how long does this cooling effect last in soil, and how will it change with the application of mulch on an otherwise bare basin? In prior videos, I observed that yes, mulch will lengthen the buffering effect of soil moisture on soil temperature. But are there some mulches that work better than others? What about the color of mulch? Are lighter shades more effective at cooling soil, and by how much? As I continue to learn how to live in a warming climate, I think these are interesting questions to explore. And the fact that we have access to low-cost, precise sensors like the BME 280 or the DS18B20 makes exploring these strategies for climate change resiliency accessible to just about anyone who has a little bit of curiosity regarding the same. And at least now, we have an instrument and code to play with, for which I'll publish details in the description of this video. In regards to improvements, it's now obvious to me that having a data logger on a staff attached to my sensors can introduce errors when the logger is being serviced. This can be easily fixed by incorporating Wi-Fi or LoRa for transmitting data to an IoT site like Adafruit.io. In fact, I recently renewed my subscription to Adafruit.io to facilitate telemetry so that I don't have to touch the instrument for data retrieval. Needless to say, the data analysis requires a more rigorous evaluation, but the fact that data is being collected is a good starting point. The data presented here is available in the description of this video for anyone who'd like to review it and/or come up with your own interesting observations or recommendations. In the interim, I'll continue thinking about new experiments and welcome your thoughts and ideas in the comment section. Thanks for sticking with it until the end. If you want to be updated on future experiments, please consider subscribing, and as always, your thumbs up are appreciated. See you next time.